Okay, we are live. Let me start the class. Can anyone confirm that the screen is visible? Thank you. Okay, so in the last class, we started a few classical ciphers. Uh, so we are focusing on classical cryptography, and I think after doing some finite field, we started with classical cryptography, this crypto system. Okay, so Uh, P is a finite set of possible plain text. C is a finite set of possible ciphertext. Key is a key space, a finite set of possible keys. And for every key, there exists encryption rule and decryption rule, which is a function. So encryption rule EK is from P to C, plain text to ciphertext, and decryption rule is from ciphertext to plain text. Such that if we first encrypt, we can use the decryption key to actually get the decryption rule to get the original plain text, right? This is the basic scenario. And we talked about you know shift cipher. I gave you an example. So basically, in most of these things, I should just say that we will be using these alphabets and the corresponding numeral values, numerical values from A to Z or A to Z from 0 to 25. Okay, and this is our alphabet mapping. So that means we are working mainly for the ring Z2 Z26 integer modulo 26, which is a ring, which is not a field. Okay, I have shown you this shift cipher, and also we talked about briefly substitution cipher. Substitution cipher is kind of a generalization of shift cipher, because you see, in substitution cipher we are taking we are mapping elements of numerical alphabets, to some other numerical alphabets, so Z26 to Z26, so kind of some permutation. And so obviously this shift cipher, is a special case, because there we are just okay, we are just shifting, so basically we are going into the same space, Z26 to Z76, right? So, and I gave you an example of shift cipher. And in most of these things, EKS is an important thing, and I mentioned earlier also, exhaustive keys search. And we want in order to decrypt. So if somehow we get hold ciphertext, so exhaustive key search from the ciphertext should be infeasible. Then only we can make sure that our system is secure. So now I'm going to define what is known as affine cipher. Affine cipher, actually, when we have encryption key something like E of x is equal to ax plus b, this is a affine function, modulo 26. Okay, ax plus b kind. Of course, a and b are in z6 z26. Okay, so this is a affine cipher. In fact, I should just mention to you again, substitution cipher is a generalization of what is known as shift cipher. And Also, it's a generalization of affine cipher. And when we take A is equal to 1 in the affine cipher, we actually get shift cipher, right? Because if A is equal to 1, it is just shifting x plus b, right, by b symbols. So basically, this is your affine cipher. Now, if encryption is something like this, ax plus b, obviously, we want for decryption affine function to be injective. You know, that is, we want the equation of the form ax plus b congruent to y mod 26 has a unique solution. Unique solution for x. We want this property to hold, that this equation has a unique solution. Then only we'll be able to decrypt it nicely. Now, ax plus b is congruent to y modulo 6 is same thing as that ax is congruent to y minus b mod 26, right? And just we are taking b on the right hand side. So as y varies over z26, right? So is y minus b varies over z26. So in other words, I can say that I am looking for, it is sufficient to study the following equation that ax is congruent to y mod 26. For some other y, but we are looking for how to solve these equations. I mean, these equations should have a unique solution. Now, there is a nice result here. I'll give you a brief proof, maybe a one side proof. Other side, I think this also is done in discrete math course, if you remember. But anyway, we will do it here briefly. So the equation ax congruent to y mod b, sorry, y mod m. So basically we have 26 here, right? Ax congruent to y mod 26 has a unique solution for every y if and only if GCD of a comma 26 is 1. This is a very important result. The equation ax congruent to y mod 26 has a unique solution if and for every y if and only if GCD of a comma 26 is 1. In other words, I would say that I can write a general result which is in the form of this lemma, right? And lemma says that the equation ax congruent to b mod y has a unique solution x belongs to Zm integer modulo m where every b in Zm if and only if GCD of a and m is 1. Okay, so in fact, why this should be true, if you remember, I have mentioned to you that whenever GCD of a and m is 1, right, so in that case a inverse exists, right? So then you can find a solution actually, right? Modulo, sorry, this is modulo m, I'm sorry, this is modulo m. Yeah, m is the basic thing because we are working on Zm or integer modulo m. Okay, so proof is just one side proof I will give. Suppose GCD is, let GCD of a and m is 1, right? And suppose x1 and x2 are two solutions. X1 and x2 are two solutions. This implies that ax1 congruent to b mod m and ax2 congruent to b mod m. That means ax1 is congruent to AX2, right? Mod m. Now this implies that A times x1 minus x2 is congruent to 0 mod m. That means this product is multiple of m, right? That means, m divides A times x1 minus x2. Now, since GCD of A and m is 1, this will imply that m divides x1 minus x2, right? Since GCD of A and m is 1, this implies that x1 is congruent to x2 mod m. So both are same, right? So we have a unique solution. If GCD of A and m is 1, we have a unique solution of this equation. So other side, so if we want to prove this side, I have first tried to establish this side. I will just say that I leave it as an exercise, but I'll just with this hint that if x belongs to Zm, then A times x takes on m distinct values mod m. So it takes every value exactly once. So I think this will give you some idea why GCD of A and M should be 1. Okay, so I leave it as an exercise for you, a good tea time problem just to think about. Okay, so I think now there is a related question. Once we say that GCD of A and M is 1, right? If A is some element of Zm, right? I mean, so what we can do here, I'm going to define what is known as Euler-Torsion function. I think we talked about it earlier also. Phi of m. So suppose A is greater than or equal to 1 and m is greater than or equal to 2. These are the integers, right? If GCD of A and m is 1, first I'm going to give you a definition. Then we say that A and m are relatively prime, right? Or co-prime, relatively prime. So the number of integers in Zm, integer modulo m, that are relatively prime to m is denoted by this function phi of m, Euler-Torsion function, or Euler phi function. Some people will say Euler phi function. Okay. So for example, if we take m to be a prime number, we know that what will be the value of phi of p? Then all integers less than p will have GCD 1 with p, because p is a prime number. So this will be total p minus 1, right? Okay. In fact, we have a general result here. If m is a product of prime powers, then phi of m, so pi's are distinct primes, pi's are distinct primes. Then phi of m is equal to partial product I is equal to 1 to n pi raised to power ei minus pi raised to power ei minus 1. This is a nice formula. Of course, EIs are positive numbers, right? Now, why this formula is useful? So basically, we established two facts. One, that this equation has a unique solution if and only if this GCD is 1. And second, that how many such integers are there which are having GCD 1 with m in integer modulo m. So this number is phi of m. So one can, now in affine cipher, actually, because encryption is AX plus B kind, right? So the number of keys, if I count the number of keys in affine cipher, then I can count using this function. So we know that B belongs to ZM, right? And so B belongs to ZM. And affine cipher is of the form AX plus B. B belongs to ZM. How many choices are there for B? M choices, right? And A is all those A's, A I need to choose such that GCD of A and M is 1. And how many such A's are possible? Phi of M. So total number of keys is equal to M times phi of M in affine cipher, right? So number of choices for A is phi of M, because we need to choose all those A's which have GCD 1 with M, right? So couple of examples, simple examples. What is the value of phi of 60? Phi of 60 will be phi of 2 square into 3 raised power 1 into 5 raised power 1 is equal to 4 minus 2 into 3 minus 1 into 5 minus 1. And this is equal to 2 into 2 into 4 is equal to 60, right? Okay. So as I mentioned to you earlier also, in integer modulo M, if A is an element of integer modulo M, inverse exists if and only if GCD of A and M is 1, right? So again, I'm mentioning this. Suppose A is in Zm, then A inverse exists if and only if GCD of A and M is 1. Okay. So A inverse exists means there exists A prime such that A into A prime is equal to A prime into A is equal to 1 mod M, right? So if you look at Z4, integer modulo 4, 1 inverse is 1. 3 inverse is what? 3. 2 inverse does not exist, right? One inverse exists because GCD of 1 and 4 is 1. And here GCD of 3 and 4 is 1. Here this does not exist because GCD of 2 and 4 is 2, which is not equal to 1. Okay. So now we are ready with the machinery. Now having, once you have these ideas, then I think you can actually do few things. So now we are looking at affine cipher. I can describe in more details. So y is equal to ax plus b mod 26 is our encryption. This implies that ax is congruent to b minus y mod 26, right? If GCD of a and m is 1, then the inverse will exist. This implies that x will be a inverse b minus y mod 26. So we can actually solve it. So decryption is possible now. So now I think we are ready to define affine cipher. Formally, affine cipher. So P is equal to C is equal to Z26. Basically, plain text and ciphertext are this. Key is from this set where A comma B belongs to Z26 cross Z26 such that GCD of A comma 26 is 1. These are our keys. And so for a key, K belongs to capital K, or I would say that for a K is equal to A comma B belongs to K in this space, we define encryption EK of X is equal to AX plus B mod 26, right? And decryption key is equal to A inverse Y minus B mod 26, right? Since I have carefully chosen A to B, these keys are chosen such that GCD of A in 26 is 1. So inverse exists, everything is fine, there is no issue. So this is your affine cipher formally, right? So because of this inverse business, I have to modify the keys here, So now once we have done this, let me give you a small example of affine cipher so that you understand it. Example. Suppose K is 7, 3, right? So note that 7 inverse mod 26 is how much? 15. So inverse exists, no issue. Encryption function will be, or encrypt function, EK of X is equal to 7x plus 3, AX plus B form, and decrypt function is equal to dk of y is equal to 15 times y minus 3, which is, if we simplify, 15 y minus 19. Now you can check that dk of ek of x is same thing as x for every x in Z26. This is easy to verify. I leave it as an exercise for you. So now, suppose the plain text is hot, H-O-T, hot. So numerical values will be 7, 14, 19 from Z26. 7x plus 3 will give us 0, 23, and 6, right? For each one, right? So this will give us encrypted values A, X, G. So this was our plain text, and this is our ciphertext. So I think decryption, I leave it up to you to verify. Is exercise for you, right? So from AXG you get this, then you use this formula to decrypt. Okay. Any question at this point about the affine cipher? Any question about the affine cipher before we move further? You can unmute yourself and ask. Any question? Okay. So we talked about 3 kind of ciphers till now. We talked about affine cipher, which is AX plus B form, right? Provided the key is a specific kind of pair of A comma B such that GCD of A in 26 is 1. This thing you need to keep in mind. So you know how many keys are there? M times phi of M, right? Number of keys are possible. And second thing, uh, we already talked about substitution cipher and shift cipher. So you can clearly see that this picture makes sense for you. Substitution cipher is more general than affine cipher and shift cipher, right? In fact, shift cipher is a special case of affine cipher if we take A is equal to 1, right? So this is how, but for doing the affine cipher, we need a special kind of arithmetic, like, we need to make sure that when the A inverse exists, then only we will be able to solve the equation, okay? So that's all for affine cipher. Now I'll go one step further and I'll talk about Wagner cipher. This is interesting cipher. So let us see what is this cipher. So here M is a positive integer, okay, and P is equal to C is equal to K is equal to Z26 raised to power M, okay. So that means for a key K is equal to K1, K2, Km. We define encryption x1, x2, xm is equal to x1 plus k1, x2 plus k2, and then xm plus km, okay. And decryption rule, dk of y1, y2, ym is equal to y1 minus k1 y2 minus k2 ym minus km, and all these operations are in Z26. Now you can clearly see that normally, so this is a generalization of shift cipher in a way, like now we are taking, every thing, has a different key actually, right? So K1, K2, K3, Km, right? So whole key is defined a big M tuple, This is kind of generalization, right? So let us take an example so that we can understand what is going on here. Example. Suppose M is equal to 6 and our keyword is CIPHER, cipher. This is our keyword, right? This implies that our K will be 2, 8, 15, 7, 4, 17. Corresponding numerical values I have written. Suppose plain text is this crypto system is not secure. Again, I am assuming that there is no space here, okay. This is our plain text. So corresponding numerical values will be 19, 7, 8, 18, 2, 17, 24, 15, 19, 14, 18, 24, right? And Now I can add, and of course I can, it's not complete yet because you see 1 2 3 4 5 6, there are so many words. So up to 24, then 18, 19, 4, 12, 8, 18, 13, 14, 19, 18, 42, 20, 17, 4. This is our plain text in numerical values. Now I have to add key. Key has length 6, right? So I am adding 2, 8, 15, 7, 4, 17, right? And I am again doing the same. 2, 8, 15, 7, 4, 17, 2, 8, 15, 7, 4, 17, 2, 8, 15, 7, 4. This is 4 and 2, sorry. This is 4 and 2. 17, 2, 8, 15. So then I can add all of this. Modulo 26, of course. So this will be 21. Okay. 21, 15, 23, 25, 6, 8, 0, 23, 23, 8, 21, 22, 15. And here if we add 20, 1, 19, 19, 12, 9, 15, 22, 8, 23, 8, 19. And here 22, 25, 19, right? Everything is modulo 26. So now I can look at this final figure here, this final figure here. And so the corresponding encrypted text will be, I'm just writing here for you. V E X Z Z I A X I V W P U B T T M Z P W I Z I T W Z T. This is our encrypted text. One can ask for number of possible keys. Is basically you can see that this is each key is m tuple over z26, right? Each choice is, so total number of choices is 26 raised to power m. Actually, just to give you an idea, for m is equal to 5, how big is this number? This is greater than 1.1 into 10 raised to power 7. So again, this is also a large number. Okay. So this is all about Wagner cipher. I think I'm going to do the cryptanalysis for each of these ciphers in my next class actually. So that's all for this cipher. Now I'll go and explain next cipher, which is Hill cipher. This is also very beautiful cipher. Hill cipher. Okay. So m is a positive number, positive integer. P and C is equal to C26 raised to power m. So Hill cipher is kind of using linear algebra. You will see that. So suppose x is equal to x1 xm is a plain text and k is a m by m matrix. So k is something like kij. Matrix you know from discrete math, I hope, and also from your linear algebra course, right? Now encrypted text is ek of x, which is y1, y2, ym is equal to x1 xm times capital K. K is a matrix. What is K? K is M by M invertible matrices. Over Z26. Now I would like to ask a question to you. I mean, first of all, let me write it down. Now for any key is something like a matrix in K, right? Ek of x, xk, and dk of y, y of k inverse. So the question is whether the inverse exists for every matrix over Z26. I would like to ask you a question. Anyone, please unmute yourself and answer. Do you think that any matrix will have an inverse? Yes or no? This is something important, so basically, so that's why I'm writing here, provided K inverse exists. And K inverse exists if some certain conditions are met, not every, because see, Z26 is a ring. So inverse may not exist for all the matrices that you, of course, in general also, inverse will not exist for every matrix if you take even if over field, right? So inverse exists only if determinant is non-singular, right? It's non-zero. Then only inverse exists, right? So here, when we say the determinant is non-singular over Z26, that means again some special condition. So let me explain to you with an example. A simple example will do the job. Suppose K is equal to 11, 8, 3, 7. It's a 2 by 2 matrix. You can check that K inverse is equal to 11, 8, 3, 7 inverse is equal to 7, 8, 23, 11. Why this is inverse? You can check that because 11, 8, 3, 7 into 7, 8, 23, 11 is actually 1001 mod 26. So this is certainly an inverse of the other matrix, right? So now let us take plain text as JULY, July. I am breaking into two parts. So JU will be 9, 20 and LY is 11, 24. So 9, 20 times this matrix is our key 11, 8, 3, 7. This is nothing but 99 plus 60, 72 plus 140 is equal to 3, 4 modulo 26. Similarly, 11, 24, 11, 8, 3, 7 is equal to 121 plus 72, 88 plus 168 is equal to 11, 22 modulo 26. Therefore, this is our encrypted text. So I can say 34 will be DE and 1122 will give you LW. So July plain text will go into DE LW. This is our encrypted text or ciphertext. Right. So I have divided into blocks depending upon size of the matrix, right? So I'm dividing to 2, 2, and then we have done the calculations. So the question is, when the inverse exists, so this is something still we need to answer. So I'm just writing the result. So remember, a matrix is invertible if determinant of A is non-singular, right? Right. So in the case of ring, what happens? So non-singular over field or whatever, right? That's something. But over the rings, what happens? So integer modulo 26, it is non-singular means all multiples of 0, 26, 52, and so on. Determinant should not be equal to any of these numbers, right? So in other words, this gives us a condition which is very, very important. A matrix K has an inverse mod 26 if and only if GCD of determinant of K and 26 is 1. In other words, it is saying the determinant of K is invertible, right? Okay, so this is a very important condition. Any question at this point? Any question at this point? Okay, so this was all about Hill cipher. So where we are using bit of linear algebra over integer modulo 26 to do the encryption and decryption, right? So I think decryption for DELW, I left it on you, so you can find out decryption rule is like this, whatever is y, multiply it with k inverse, and you get the answer, right? This is how you do it. Okay, so now I am going to describe another cipher known as permutation cipher, or also it is known as transposition. Okay, permutation cipher or transposition cipher. What is this cipher? Let me look at it. So what is a permutation? First of all, let us look at an example of a permutation. Suppose m is equal to 6, x is a number 1, 2, 3, 4, 5, 6. It's not number, but this vector. And pi of x is permutation of x. 3, 5, 1, 6, 4, 2. In mathematics or in algebra, we normally denote it by 1, 2, 3, 4, 5, 6, 3, 5, 1, 6, 4, 2. This is the permutation. The image of permutation is a one-to-one and onto function which is taking elements. So 1 is mapped to 3, 2 is mapped to 5, 3 is mapped to 1, 4 is mapped to 6, 5 is mapped to 4, and 6 is mapped to 2. Okay, this is an example of a permutation. Okay. So I think now I can write down pi inverse permutation. So if x is, so basically I can write it down 1, 2, 3, 4, 5, 6, inverse is 3, 6, 1, 5, 2, 4. Okay. This is the inverse permutation. So basically pi into pi inverse is the identity permutation. 1 is going to 1 and so on, anyway. So for example, 1 is going to 3 and 3 is going to 1. So it is going to 1 and 1 is going to 1 in the first one. Similarly, 2 going to 2, 3 is going to 3, 4 is going to 4, 5 is going to 5, 6 is going to 6, So now let me write down the formal definition of permutation cipher. And so if m is a positive integer, P and C is our plain text space and ciphertext space is this. If K is all permutations of the set 1, 2, 3 up to m. So for a key pi is a permutation. We define e pi of x1, x2, xm is equal to x pi of 1, x pi of 2, x pi of m. This is the permutation. And decryption rule, y1, y2, ym is equal to y pi 1 of inverse and so on, y pi inverse of m. Pi inverse is inverse permutation. We just saw that, right? So permutation cipher actually is a special case of Hill cipher. And the reason is because the corresponding matrices, permutation matrices, are special matrices, right? So let me do the example. Plain text. She sells seashells by the seashore. So we can divide it into partition. We first partition it. She sell LSSEAS HELLSB YTHESE ASHORE, right? For pi that we saw, this pi actually, so we can apply one goes to third position, second goes to fifth position, third goes to first position, and so on. Okay, so this will be EESLSH SALSES LSHBLE HSYEET and HRAEOS. This is your encryption. Okay, we have moved the positions, and I have written the capital letters just to show that this is ciphertext. Okay, so this is a important thing to observe. I'll just mention one final thing before we close. For a permutation matrix, for a permutation pi, one gets permutation matrix actually. K pi is equal to Kij. Kij is equal to 1 if I is equal to pi j and 0 otherwise. Okay. So for our permutation, K pi is 0 0 1 0 0 0 0 0 0 0 0 1 1 0 0 0 0 0 0 0 0 0 1 0 0 1 0 0 0 0 0 0 0 1 0 0. That's the permutation matrix for the permutation that we described here. This permutation 1 2 3 4 5 6 3 5 1 6 4 2. Okay. Any question at this point? So I think if there is no question, I will stop. And so we have got a couple of ciphers today. You can actually go through it, and then there will be exercise or something which you can do so that you know more. Thanks, actually.